Good morning, guys. Today we are going to look at a new section in calculus called advanced integration techniques. So these are real algebra heavy moves for composite integrals. So before we get started with showing you how to integrate, let's remind ourselves essentially how we derived composite functions. And I think that's going to help you see the process a little easier. All right, so for our first one, we have the sine of 3x. Any composite function, you know that you start with the outermost function, sine. So the derivative of that is cosine. We, of course, know that we're going to leave our argument 3x exactly the same, and then we multiply by a 3, so because that represents the derivative of our argument. Moving on to the next one, we've got an outer argument of e and an inner argument of cosine x. So we start with the outside, the derivative of e is e, leaving our argument the same, and then we multiply by negative sine x. For our number 3, we have the natural log of x squared plus 3. Anytime we're deriving the natural log, sorry about that. That's just 1 over your argument. And then we, of course, multiply by the derivative of our argument. You could simplify this to 2x over x squared plus 3. Finally, we have f of x is the square root. Think of that as x squared plus 3 raised to a power of 1/2. Makes it a little clearer there. The inside function is x squared plus 3, and the outside function is our 1/2. So we've got, we're going to use power rule. 1/2 comes down, x squared plus 3. Our new power is negative 1/2, and then we multiply by 2x. Again, you can simplify this to 2x over 2 square root of x squared plus 3. So again, the reason why I'm showing you how to derive composite functions is because now we're going to integrate these same functions. And so if I were to integrate 3 cosine of 3x, we know that this is going to be equivalent to our original function f of x, so the sine of 3x. So essentially, hopefully you're like noticing what happened to this original 3? Where did it go? It disappeared, right? And same is going to be true for these following ones. If you take the integral of e to the cosine x times negative sine x, that's just going to be your original function, e to the cosine x. So again, this term right here kind of drops out altogether. It's not even a part of our answer. Same goes for the third one. If you were to integrate 2x over x squared plus 3, you're really just treating the denominator here, so that would give us the original function, the natural log of x squared plus 3. So again, you're probably thinking, what happened to the 2x? Why is it not a part of our answer? And finally, the integral of 2x over 2 square root x squared plus 3 is just our original function, x squared plus 3. So you see this part in our integrand, and it moved up, so it, they probably applied a power rule in there. But again, the 2x is completely gone. It's missing. And again, this is all a result of the chain rule. So anytime you have an integrand, hang on, let me back up a second for a minute. We have the derivative rule for f of g of x. Sometimes you'll see this written as f of u meaning some inner argument. And we know that the derivative rule for that is f prime of g of x, keeping that argument the same, times g prime. If I were to write this instead using u, we would call it f prime of u times the derivative of u, or du dx, right? So therefore, when we work backwards, you will often have integrands that have two parts to them. One part of your integrand, and I'm highlighting this part, represents the derivative of the other part. The derivative of the inside part. And so when that is the case, you literally just kind of ignore that second half and you just integrate the outside function. So the integral of f prime we know is f, and leave the argument the same. So a lot of the game here is training yourself to ignore du, ignore the derivative of the argument. Let's do some examples together now that I've shown you like a pattern here. Okay, so in example 1, the first thing that you want to recognize is who is the composite function, right? Who is the argument? So in this one, our argument is x squared plus 1 because there's another function on the outside of it, right? So we're going to call that our u. Okay, and then we're going to take the derivative of u, with respect to x. And the derivative of x squared plus 1 is 2x. Now, because we have a dx over here too, I'm just going to move this dx from my denominator over onto the right side. So we have du equals 2x dx. This is also a part of my integrand. And now we're going to perform something called u substitution. So I'm going to replace x squared plus 1 with a u. And remember, there's a squared on the outside, so my u needs a squared on the outside as well. And then 2x dx, that is the equivalent to du. And so now I've really simplified this integrand, right? It is just a power rule function. We know how to integrate something like u squared. We know that we would apply a plus 1 power to that, so that would make it a 3, and then we would divide by our new power. So our antiderivative is 1/3 u to the third. And then du is just a notation thing. You don't have to worry about integrating du. It's just saying with respect to u. And now we're going to change u back to its originally assigned value, x squared plus 1. All right, as always, I put the plus c on the end, by the way, because it's an indefinite integral. All right, and so as always, it's a good rule of thumb to check your function to see that the derivative of your function is your original function, which it is. Let's do another one. All right, example 2. We've got a function 5x squared plus 1 on the inside. We've got a squared on the outside. So we know that u is going to be 5x squared plus 1. du with respect to x, the derivative of u with respect to x is, what's the derivative of 5x squared plus 1? 10x. And again, I'm going to move my dx over because in an integral, the dx is attached on the right. So the derivative of u is 10x dx. Okay, now we can make our substitutions. In our integrand, we have 5x squared plus 1 squared, so that is u squared. And over here, we've got 10x dx, which we know that is the derivative of our argument. And so essentially we're just rewriting the integral and allowing ourselves to ignore du, the derivative of the argument. Okay, now we can integrate as normal. The integral of u squared is 1/3 u cubed plus c. And now we can replace u back with 5x squared plus 1 cubed plus c. All right, I'm going to have to pause this video so that it doesn't go longer than 15 minutes, and I will post part 2 shortly.